First of all, I would like to thank the organizers for giving me an opportunity to present this kind of a work here in a statistical physics meeting. So, but I would like to state that at this point of developing a research theme, I feel the need to come back to the statistical physics community and learn a lot. Last 2 days, I've been learning a lot of new things, which has equal contributions in the development of this theme, which is a combination of general relativity, basic principles, and borrowing basic principles of statistical physics and extending them for a underlying space-time structure. The motivation for developing this kind of a theme comes from the interest in exploring the properties of dense matter relativistic stars. Dense matter exotic matter is not yet fully understood. There are lots of efforts going from nuclear physics details towards hydrodynamics and the GR community. The interest in mesoscopic scales in dense matter stars is comparatively new, and the first results and the first interest towards mesoscopic scales in asteroseismology arise from pinning effects in basically pulsar glitches, which also have observational effects. These were the first results in exploring the mesoscopic scales for dense matter stars. Fluctuations in relativistic fluids is another area where mesoscopic range physics and relativistic theories are coming up, and they are of immense interest, current interest, and hold a very large scope in theoretical developments as well as observation consequences as well. Turbulence in relativistic stars is comparatively a new area. Basically, I would not go towards the developments in relativistic stars, but come down to a very new formulation. As I said, the Einstein-Langevin equation, where the basics from the statistical physics theory are used. So these are pictures, these are standard pictures of turbulences in terrestrial fluids. You can see these vortices, and these are the sources of stochasticity in the velocity field in a fluid. Okay, and why am I showing these is that these are regular things, but if you go to astrophysical systems, they are generally assumed to be spherically simplistic, and there's a geometry, so there'll be a pattern how these vortices will be distributed and giving rise to stochasticity. So there will be a pattern, but the importance of capturing these stochastic effects is that these stochastic effects will give rise to perturbations in the systems. So let me begin. There are going to be 2 slides where the basic new formulation I'll present in this 10-minute talk. So I'll begin with the Einstein's gravitating systems, which are massive, are governed by Einstein's equation. Asteroseismology, which is basically the study of oscillation of stars, which through which we can probe the interiors of the dense matter or whatever they are composed of, is based on the perturbed Einstein's equation, where this is the Einstein tensor, which is basically comes from the space-time geometry, and these are the matter fields, often modeled as perfect fluids. So this is a combination of fluid mechanics, GR, statistical physics concepts come in with a new linear response relation is proposed between functions of matrix. So HAB I denote here is the perturbation of the space-time metric, while psi A is in Lagrangian the matter field displacement vectors. So the Einstein's equations, when you perturb it, there are 2 fundamental variables of perturbations. One is the metric part and one is the matter fields part. Model in terms of fluid, I will restrict to fluids over here. So this is fluid, you can take this as fluid displacement vector. Okay, I'll show you the form of the TAB which can be used. A new linear response relation is proposed between functions of metric perturbations and the fluid. So I've divided this whole system as the space-time metric and the fluid degrees of freedoms. So, and the perturbations are divided. So this is the metric, this is the matter fields, and they are combined together in a linear response relation with a response kernel, which you see is very different from what you usually take in a statistical mechanism. This is the space x and x prime denote the space-time variables, not just the time or space. So this is extension of the concept of linear response kernel for an underlying space-time structure. So this thing is defined on a space-time manifold. Okay, so this is the very new formulation which has to satisfy the properties of covariant this equation. If you put this particular form for the Einstein's equation, this is phenomenologically proposed. So it looks like this. And because it is Einstein's equations and on a space-time manifold, it should be covariantly conserved. So the covariant, if you apply the covariant conservation property here, there's a restriction on this response kernel such that this has to be x minus the k. This is general. In general, if you take in a curved space-time, there is no need for it to be x minus x prime. It has to be at 2 points. But if you want this equation to satisfy the covariant conservation property, which is necessary for any system governed by GR, this is the form which is expected, which also tells you that this kernel, this separation between x and x prime has to be in such a region where you can take a flat space-time approximation only, which is very much valid in case of relativistic stars, because usually they are governed by Einstein's equation, but for a very long distance you can take flat space-time. Say half of the radius of a neutron star. So neutron stars is like about 10 kilometers. On a global scale, of course, it needs GR, but on a smaller scale, if you want to take, say, a shell of some thickness, then this x and x prime will denote the R1 and R2. So how much of the shell you can take. So that is the restriction on the response kernel here for a space-time structure. And yeah. And so that's not all, that's just the linear response kernel. The Einstein-Langevin equation is completed when you add a source of noise. And remember that this noise, tau AB, is that of the matter fields, which the things are which the star is composed of. Where I said that when I show you a picture of the turbulences and the source of stochasticity basically comes from the superfluid state where turbulences takes in the velocity. So I've shown you I'll show you an example of TAB for a relativistic star, but this is basically a stochastic term, which is defined on the background unperturbed spacetime. This G is the unperturbed spacetime and H is the perturbation to H. So it is the background, the noise is defined on the background which feeds the system such that it is perturbed. The Einstein's equation is perturbed in this way. So this is the full form of the classical Einstein-Langevin equation. Now this idea of classical Einstein-Langevin equation follows from a similar theory in semi-classical stochastic gravity, which is aimed at early universe cosmology, which is mathematically and astrophysically also very different. I have just borrowed the overall idea of an Einstein-Langevin equation for classical systems only, which is applicable to massive relativistic stars. So this is the form, this is the new formulation in general relativity also, which uses the basics from a stochastic theory of stochastic processes. So there are lots of properties that these noise and this kernel should satisfy, which should be consistent for applications to different relativistic stars is one of the applications. You can apply it to more systems like cosmology also. That is the second idea, so the second application to it would come up. So this basic construction in GR with yeah. So this is the crux, and the noise basically, as the statistical physics community will know, the 2-point correlations are the most relevant things when you analyze stochastic processes, and they help you to probe regions, extended regions in whatever system you're studying. So I'll just come to, so for example, I've given you this example of, I said the matter stress tensor, for example, a perfect fluid, if you take, this is the stress tensor. And with this you can form the noise also, the background noise, for example. If you take the fluctuations in the velocity given by this, and you put in the Einstein's equations and solve them I have solved them analytically for the simplest toy model of a spherically symmetric relativistic stars with velocity fluctuations. And here you can ignore all these detailed quantities. What I want to show you is this is the Lagrangian displacement vector. So of course the expectation will be 0. It is the 2-point correlation which is meaningful, which gives us the meaningful result, and they lay the foundation for non-equilibrium as well as equilibrium statistical, doing statistical physics and probing the properties. So these lambda, delta lambda, these are the potentials, the metric potentials, what I do HAB in case of spherically symmetric matrix, where it depends on R1 and R2. So this is the form. So you see that the 2-point correlations of the matrix depend on the 2-point velocity fluctuations in the background of the star, and this feeds in. So you can have estimates, and even for more complicated systems like gravitational wave detection and all, they are based on detecting the matrix perturbations. So these will be mild. We don't worry about the magnitude, but these are the new qualitative result, where you will see that the 2-point and higher correlations of perturbations from the base of a statistical analysis for perturbations, equilibrium and non-equilibrium properties of dense matter can be analyzed, extended non-local structure. And turbulence and vortex filament structure inside the dense matter can be investigated model using velocity. Velocity as well as pressure and energy density, the stress tensor variables, any fluid variables. This is just one example velocity I'm saying. And so observationally, I would expect that this is if this large thing, this is the gravitational signal, the stochasticity would look like this on that. And challenge in the scope of the research program is to build a subhydromesoscopic theory for dense matter compact matter related stars to investigate in detail velocity, pressure, energy density fluctuations and the correlations in dense matter, which is not done yet, and it is a very desirable development if you can have a theoretical formulation to analyze, investigate such things. So this formalism acts as a probe to investigate the nature of dense matter, which I think everyone is interested in. So numerical modeling of stochasticity and generalized stochasticity is a big challenge over here, but with the potential of wide scope in research and applications of general relativity. And that is where the role of people in statistical physics and the methods of modeling stochasticity are going to be very useful and helpful. If you extend it for space-time structure, or you can have 3+1 split space and time. So there are lots of schemes can come up. Theoretical and foundational level mathematical developments using basic new ideas from complex systems, statistical physics, fluid mechanics need to be extended for space-time with focus on dense matter applications and more. So these are the basic principles, as I said, with this way about the beginning of a new and exciting theme of research. Presently open for theoretical foundations. We are not bothering about whether they are of observation consequences right now, because these are qualitatively and mathematically new results. These include GR, statistical physics, fluid dynamics, and stochastic force. Thank you.
We'll take one quick question.
Yeah.
Thank you. When you say it's a perturbed equation, do you mean just in the energy momentum tensor or also in the metric?
Oh, it's also the metric. It's the full Einstein's equation is perturbed, as I showed you. The feedback is due to this noise, but the whole of the Einstein's equation is the new thing. There are two new entities here. One is the response kernel, how the metric perturbation, and the second is the noise, which is in the background. So the whole of the Einstein's equation is perturbed with something feeding into it is induced perturbations. The source of perturbations are the fluctuations, but the whole of the Einstein's equation is perturbed.
So the metric can vary with time. There's a time component also, non-zero time component.
Yeah, there's a time component. So what I showed you the results, the metric perturbations, the mathematical results. They are basically, say if you take a spherical symmetric, then there's a radius and time. Yeah, the 2-point correlations between T1, T2.
And if you're an asymmetric metric tensor like some Finsler geometry or something like that.
So it is a general result in GR. You can take any geometry and have these results. The thing is that analytical solutions won't be possible. You will have to go to numeric. That is further program. Numerical relativity you have to use to solve further more complicated like rotating geometry and other geometries. But it's a very general result, the general formalism, which is applicable to everything. And that's the basic interesting thing we can, yeah.
Okay, let's thank our speaker.